Okay, let's start. Here we go. Ready to start. We're turning in homework, right? Did you collect homework? Guys. Okay, so we said that so much of this boils down to kind of one central idea, that if a function is increasing, then the derivative or the rate of change is positive. And if the function is decreasing, then its derivative or rate of change is negative. And so like 75 to 80 or to the 85% of it just boils around that central idea, because then when we move to the first derivative and compare that to the second derivative, well, the exact same relationship holds, because the second derivative is just simply the derivative of the first derivative. Okay? So if the first derivative is increasing, then the second derivative is positive. And if the first derivative is decreasing, then the second derivative is it's the same relationship, because you could just think of that first derivative as its own new function, and then the second derivative is simply the derivative of that, the rate of change of that one. Okay, so I'll go through this. You can listen to me reason through it and compare it to your reasoning. So this is the rate of change function, and we want to sketch the original function such that this is the derivative of the function we want to sketch. Okay? So am I going to be focusing on where this is increasing or decreasing, or am I going to be focusing on where this is positive or negative? If this is the rate of change, positive or negative. What I'm drawing is going to be increasing or decreasing based on where this one is positive or negative, right? Just that goes back to that same principle. So here it is positive, and so we don't know where it starts. We don't know, because this is just the rate function. Here at 2, the amount of accumulation could be anything, so I'll just start here, say. Okay? Doesn't matter. So from 2 to about to about negative 1.5, this function, this rate of change or derivative is positive, so my function will be increasing. Okay, until the rate of change is 0. That means I get a pause. There'll be a pause in the function I'm drawing because the rate of change is 0. And then what happens after that? Right, so again, through this whole thing, this is all positive here, so my graph is just going to keep going up all the way until here. And what about here? It's going to be increasing at the highest rate here. So my slope is going to be the steepest when I get to this value right here. So something like this. And then it's going to pause where the rate is 0. Okay, and then what's going to happen through here? The rate of change is negative, so the graph who has this as its derivative, the accumulation function, will be decreasing, and right about here, decreasing at the fastest rate. So now it's decreasing the fastest rate, and then decreasing less, something like that. So because I'm given the rate of change function, I'm focusing on where that's positive and negative. That's going to determine where my graph is increasing or decreasing, and then where the rate is 0. is where I'm going to get a pause, where my y value is going to hold steady for just a moment. Okay, questions on that one? Does it make sense? Okay, now do it again. But now this is the first derivative, and I'm going to draw the second derivative. This is the first derivative, and I'm going to draw the second derivative. So, how am I going to think about this now? Am I going to be focused on where this is increasing or decreasing, or where it's positive or negative? Increasing or decreasing. So I can forget about the fact that this is a rate of change function. Why? Because I just want to take this function and sketch its rate of change. Because that's how the second derivative relates to the first derivative. So forget about the fact that it's a first derivative. Forget about the fact that it's a rate of change. I just want to sketch the rate of change of this one, like it's an accumulation function to start with. So I'm going to be focusing on where this one is increasing or decreasing. And wherever it's decreasing, I know that I'm going to be negative, right? And wherever it's increasing, my rate of change or my derivative will be positive. So, and then wherever it's 0, or let's see, wherever we have a pause, what? So wherever this function pauses, my rate of change will be 0. Let's just start with that. Wherever this function pauses, my rate that I'm drawing, the derivative of this, will be 0. So let's just start with those 3 points right there. And so now I know that this is decreasing. So my rate is negative. And then it's increasing. So my rate is positive. And here it's increasing at the fastest rate. So this is kind of where the high point of the rate will be, right? So the rate is increasing. Here's where the rate is highest. So my rate of change, that's where it's highest. Okay? And then what's happening through here? All through here it's decreasing. And again, it's going to be decreasing the fastest right here. Something like this. Until the accumulation or this function pauses, so the rate is 0, and then it's increasing. So this is going to flatten out, all the way flatten out, because the given graph pauses, the rate is 0. Oh, let's see, does that necessarily flatten out? No, okay. Okay. Questions on these sketching problems? I'm sorry? Yeah. Thank you.
Another strategy we can use is to take small changes of x and collaborate at that on the graph that's given to us to try and sketch the.
Okay, so you're looking at a small change in x, and then kind of estimating what that rate of change is, and then plotting a point. Yeah, it's okay.
Yeah, I was doing that too.
That's okay. But do you see how my strategy works for this particular situation? This is kind of a quicker way to get just something general. That's going to get you something kind of trying to get more exact. That's okay. All right, questions on that?
C, please.
Oh, C. Well, I can't do C because I don't have them both showing. But the idea is that if this is now this is the second derivative that I'm comparing to. Well, let's see if I can do it fast. So how fast can I do this? Let's see. What did it look like? This was negative. I can't do it that fast. But anyway, this is going to be the original function that you drew here, and this is going to be the second derivative that you drew here. So wherever this one is concave up, this function should be positive, the one that you drew. And the one that you drew, wherever the one you drew is concave down, the one that you drew here should be negative. That was the point of that. So you're just looking at those intervals and saying, okay, in this interval, My original function's concave up. Therefore, in that same interval, what I sketched, that second derivative should have been negative. And then you go interval by interval like that. And that's the way you kind of are reasoning that you're checking them against each other. Okay, other questions? Okay, so now we're entering this part of the course where see, am I in the right place? No, I'm not in the right place. Okay, so this part of the course is we're going to do these optimization application problems. Lots of students pulling their hair out over these. Okay, really hard, and it feels like, oh, they're all different. Everyone's different. You get one that's trig, then you get one that's geometry, then you get one that's economics, then you get one that's, you know, they're just all different kinds of problems. So I'm going to try to give you a way to imagine, a mindset to have for every one of these optimization application problems. So what we talk about at first is going to be true for all of them, okay? Or kind of the way you're thinking about all of them, and then we'll start looking at some different examples. Okay, so with a function, so this is our mindset about optimization. This is kind of the mental image you'll have when doing these problems. With a function, various values of the input quantity can be chosen. Okay, each one resulting in some corresponding output. Old hat, right? This is all. That's review. This is what functions are about. You choose what your input is, or we let the input increase starting at some value, and then for every current value of input, we get some corresponding output. And this curve is just the collection of all those points, right? So the question is, how to find the best value of output. Which value of input should be chosen? So we're trying to find something that's the best value of output for our situation. Okay? Then the question is, which value of input should be chosen to do that? To get our best value of output. Okay? So to answer this, we'll need to know two things. First thing is, we'll need to know what is meant by the best value. Are we talking about the maximum or the minimum output value in a given situation? So sometimes it's maximum, sometimes it's minimum. All right, and then the second thing we need to know is what interval of input is relevant, and we'll call that the applicable domain. So what interval, given the situation, this real-world situation, what interval is going to apply to the situation? And once we know those two things, then we can isolate that interval, analyze the function to find either the maximum or the minimum within that interval. Okay? And is it the maximum and minimum input or output? Output, okay. So I would call this an accumulation function, but it's possible that we want to maximize or minimize a rate function too. Okay? That's possible, that the output could be rate of change, or the output could be accumulation. Okay? Okay, so let's try some just visual examples here. Okay, so what input value would result in we'll start with max, okay? The max value of output if the applicable domain is, say, from 0 to 30. Can you read the numbers on the axes? Is it big enough? So what input value would result in the max value of output if the applicable domain is only from 0 to 30? So it's just like we don't care about this part of the graph. Just going to erase it. So all we care about is the part of the function from 0 to 30. And so what do you think? What value of input? Around, we're just estimating here, just to get the idea, would result in the max value of output if the applicable domain is from 0 to 30. I hear 6, 7. 6 or 7, that's right. So 5, 6, 7, somewhere in there. It's actually like 5.5. Okay? And then, what is the maximum value of the output? What is the maximum value of output? Is it 5.5? No, what is it? 4.2. Yeah, f of 5.5. So f of 5.5, or around 4.2. So 5.5 is the choice we make. So in these real world situations, it's like we have a choice. We can choose all these different x values from 0 to 30. Which one should we choose to make the output the biggest? All right. So we're going to choose the input to be 5.5, and then we're going to to get that maximum value of output, it'll just be the output of that function, or f of 5.5, or around 4.2, 4.3. Okay. So how would we isolate? Then algebraically, how would we hone in on that 5.5? So I'm giving you a visual mindset, but when you do the problems, it's all algebraic. It's very little graphing until the end. Okay? So now we got to think about it. If we just had this function f, and we didn't have this graph, okay, how would we find and isolate that x value that would be our choice, 5.5? What would we do? Dima? Substitute? But all I have is this function. I'm trying to figure out how to get that 5.5. So I just have this f of x, which is, some sine or polynomial function or something like that. How am I going to figure out what that 5.5? What's that? Local max. How do we get a local max? Right, so a local max is going to be where this output pauses. And we know that that's where the first derivative, we want the critical values, right? So I'm going to take the derivative set equal to 0. And I'm just going to solve that, and I'm just going to get 5.5, right? No, what am I going to get? I'm going to get 5.5 and like 16 and about 24 or 25. So, so I just got 3 values. How am I going to know that 5.5 is the greatest, the maximum? Yeah. Yeah, so yes, exactly. So what we do is we get candidates, right? So it's like we'll have candidates for our x value that might give us the maximum. All right, so we would compare. So our candidates would be x equals 5.5, 16, and 25, and then we could just find the output of each one. And then what are we looking for? Greatest value of output. Greatest value of output. And when we'll plug f 5.5, we'll find that one's the biggest. And we'll know that we have the maximum value. Right? Does it make sense? So again, I'm giving you a visual mindset for these problems, but when you do them, it's going to be very algebraic. You're going to be working with the functions. You're going to be taking derivatives, and it's all going to be about numbers and symbols. So try to really retain the thinking behind it. Okay, so let's try a new interval. Okay, so we want to find the max again. And now I want to go from, let's say, 10, x equals, say the applicable domain now is 10 to 35. Okay, so there's 10, and then from 35. So now what applies in this context is that x would start at 10 and end at 35. And I want to find the max value of the output. So I'm going to do the same thing, right? I'm going to take the function, find its derivative, set it equal to 0, and what will happen? What will I get?
16.
Well, actually, I'll get the same 3 values again. I'll get 5.5, and I'll get 16 and 25. But we look, and what happens here now? Yeah, so now we're going to, this is not in our applicable domain. So now we're just choosing between 16 and 25. And what's the maximum going to be? So we're going to pick x to be 25, right? Who said no? You said no. He said no. He said no. Adrian, why? Because that's not the highest point. What's the highest point? I thought it was the local maximum.
10 is
We want the highest value. Okay? So what's the highest? Where do I get the highest value? 10. 10 is giving me the max in this situation. If my applicable domain is from 10 to 35, I really need to check 10. Okay, so what I need then? Do I need to check every point? Do I need to check every point here then? Because we just saw that. Okay, it doesn't have to be a local maximum. It could be something else. Let's look at a different situation. How about this? How about we're going to do max again. X from 15 to 24. Okay. Talk to the person next to you. How am I going to, what's going to be the X value to maximize the output of F? Go, talk to the person next to you.
how much distance is above the x-axis. And 24 appears to be the most distance on the x-axis.
Okay, what X value is going to give me the maximum output if I'm only considering from 15 to 24?
24.
24. Right here. And what is the value of the maximum output?
F of 24.
F of 24 is the max. So x equals 24 is the choice we make to get the maximum value of f of 24. So we're seeing two different possibilities. So let's do a minimum example now and see if we can summarize what's going on here. So let's do, how about, we want to find the minimum, the min value of output from, let's do 0 to 30 again. So that's what we started with for max, right?
Correct. It's the first interval we did.
Now I want the min.
The minimum.
What should we choose and what's the value of the minimum? What should we choose and what's the value of the minimum?
30.
We should choose 30 and the value of the minimum is?
F of 30.
F of 30 or whatever that is, around 2.5, 2.4. Okay, another min example, and then we'll summarize. How about from 0 to 25? Go. So what should I pick? And what will be the value of the min?
Somewhere around 70.
Okay, so the x value that we should pick would be
16.5.
16-ish, and then the value of the minimum, or the minimum value would be f of 16. Okay, so if we were coming to this problem and we had f, but we did not have the graph, can we have a system so that we have all possible candidates for, say, a minimum or a maximum? What system could we devise so that we would know that the maximum or the minimum has to lie in this list that we're going to make of possible candidates? So what's one possible arena of candidates for a maximum or minimum? Yeah, f prime is 0. So the max or the min will come from x values at, said f prime is 0. What do we call those? We call those critical values. F prime of x equals 0 or does not exist. All right, or what? Yeah, so we saw that we got these situations where at the end or the beginning of the domain you could have a high or low point. So we'll call these the endpoints of the domain. Okay, so what are we going to do? We're given a function. We won't have its graph. We'll know what the domain is. We'll first find all the critical values within the domain. Those x values will be possible candidates for the max or the min value of the function, the optimal values. And then we'll look at the endpoints of the domain, and we'll throw those into the list as well. So all the critical values, the x values of the critical values, and the x values of the endpoints will be our list of potential candidates for absolute max or min. And how will we know then? How will we know which one to pick? What's that? So like in this case, if we didn't have that graph, we would come up with, what x values would we come up with in our list? So suppose we didn't have the graph. Okay, x is 0 is 1. What else? 25. We're going to... Okay, and so what x values were those? About 5.5 and 1625? Oh, so did I happen to cut that off at a max? All right, so we already got 25 because it's the endpoint. Okay? So say we're going from 0, it doesn't matter. Okay. So yeah, so we're gonna make this list of potential candidates for max and min, and that list will come from critical values and endpoints. And then to figure out which x we should choose, what do? Yeah, we're going to just find all those output values. The output value that's the largest would be then our maximum value, and then we would choose that corresponding x value. The output value that's the smallest, so we're going to look for the max and min of those output values, and that tells us what we should choose for x to maximize or minimize this function over the applicable domain. Okay, so this is the mindset that you have without the graph, and it's just going to be equations and numbers and symbols, right? Okay, but so the hardest part about these, so that's kind of like less of the harder part. Once you understand that, the hardest part about these is, okay, so one more time. Review. What are we trying to do? We're trying to find the best output and we're going to figure out which value of x we should choose. So what makes these problems hard is this. Every optimization problem is about defining and using the function whose output is the quantity to be maximized or minimized. And defining this function is where these problems are difficult. Coming up with the function. But the whole problem revolves around that function. Everything we do revolves around that function. The solution, creating the function and then using it, finding the derivative, setting it equal to 0 to get the critical values, plugging in our endpoints and our critical values to get our possible candidates for max and min. All right? So the whole problem revolves around this function, and creating it, defining it is usually the hardest part about these problems. Okay, so let's try some examples. We'll start with more easy and then get more difficult. Okay. Example 1. What two non-negative numbers, a and b, whose sum is 25, maximize the value of 2a squared plus b squared? And then we can also talk about minimize. Okay, so what two non-negative numbers, a and b, whose sum is 25, maximize the value of 2a squared plus b squared, and then minimize the value of that expression. Okay? So what is the central feature of this problem? What is the central feature of this problem?
2a squared.
There's an equation.
What's that?
There's an equation.
An equation?
To 0.
An equation that we're going to set equal to 0. That's the central part of this. What do you think? What's the central focus of the solution? I just told you. But I thought it might have slipped your mind. A function whose output is the quantity to be maximized or minimized. A function whose output is the quantity to be maximized or minimized. All right, so what do we need? We need a function. F of, so the question is, f of what? And the output is the thing we're trying to maximize or minimize. Well, so what expression are we trying to maximize or minimize? 2a squared plus b squared. Okay, so that's a great start. It's like they're giving it to us, right? They gave us the hardest part. They just gave us that thing that we're trying to maximize or minimize. But there's a problem here. So what do we have? When we have our, like with that previous example with the graph, what do we have? We had one input x and one output y. How many inputs do we have here? 2. So once we get this initial kind of expression, oftentimes this will have more than one input, and we need to get it into one input. So we can choose A or B. Let's choose A. I like it. So we need to get this thing to look like an f of A, meaning that 2a squared plus b squared needs to be entirely an expression of a's. Well, the 2a squared is fine. So we got to deal with the b squared. So what we need to write b in terms of a. Can we write b in terms of a? And then if we had that, we would square it and we would have our function. So what is b in terms of a? Or what will help us find that? Well, we have some more information here. Whose sum is 25. A plus b equals. Okay, so this is like side work. Okay, this is side work. The central focus is our function. This is side work to help us complete the function. And what do we need? We need b in terms of a. What is b in terms of a? 25 minus a. And in our expression, it's b squared. Now we've got our function for whose output we're trying to maximize or minimize, and we've got it in one variable. Okay, so what we just did in this problem is the hardest part of these problems. I mean, so this is an easy one, okay? When you get these complicated geometry problems, trig is involved, okay, and there's lots of quantities flying around, coming up with this is the hardest part. And then from here, it's what are we trying to do? We're trying to maximize. So what we need the applicable domain. What's the applicable domain? Or all possible values of A. So it says two non-negative numbers whose sum is 25. So A could be as... So we're trying to figure out what the lowest value of A is and what the highest value. So what interval of A do we have that meets the conditions? So A could be as low as 0, non-negative. And what's the highest value of A that we could have? So the highest value of A is when B is the lowest, right? So B could be as low as 0 also. That would make A. All right, so we got it. We got our function that we're trying to maximize or minimize, the output, and then we got the applicable domain. And so to find the max or min, what do? We just laid out a roadmap. We're going to look for our candidates are going to come from two possible places. Our candidates are going to come from critical values, local maxes and local mins, and endpoints. Okay, so our candidates 0 and 25. So candidates for max and min. 0, 25, and let's see if we have some more candidates, and we're going to find those by taking the derivative. F prime of A equals 4A plus 2 times to the first times -1. Oh, masters of derivatives. That's how fast you should be able to do it. Okay, and what are we going to do with that? Looking for critical values, where our function is going to pause at a high point or a low point. So it equals 0. So we're going to have 4A minus 50 plus 2A. So we're going to have 6A equals 50. So we get one critical value at 50 over 6. So there's only 3 possible candidates for max or min. There's one critical value. So we should also check, is 50 over 6 in the domain? Does it fall between 0 and 25? Yes. So we're going to keep it. Okay. Any critical values that don't fall in the applicable domain, we chuck them out. Okay. We only want all the critical values between our endpoints. So again, endpoints, critical values. And then how do we find which one to pick to maximize? Yeah, we want to find the value of the output, right? We're trying to maximize the value of the output. So we're going to put it in. Put 0 in here and we get 0, 625.
Mr. Ashbrook?
Yes, please.
The 50 over 6 is supposed to be negative.
No.
Wait, what?
Must multiply by
No, so I have positive 6A here on the right and would be positive 50 on the left. So I just changed the order. Yeah. They end up being the same. When you move all the A's to one side and the 50 to the other, they're the same sign. Okay, so f of 0 I think is 625. Check my math. Is that right?
Yes.
And then this is 1250. And then this one I can't do in my head. So 50 over 6. We're going to put that in. And we think, graphing calculator, right? So we're going to have so here's the way to do this. F of A equals 2A squared plus 25 minus A squared And then f of 0. Boom, 625. F of 25. Boom, 1250. F of 50 over 6. 416 and 2/3. Okay, so you see how powerful graphing calculator was there and function notation?
Yes.
Function notation represents output, right? And so if you define the function and then just tell a graphing calculator, find me this output, use function notation. Find me this output. You don't have to do anything. You don't have to do any calculations. Okay? All right. So, maximum. Well, you can use it on your homework, and that's going to be a lot of time. So yeah, use GC. It's a lot more, does a lot more, a lot faster than a handheld. Okay, so maximum occurs at 25 at the right endpoint. Okay, minimum occurs at our critical value. So that must be a local min, because on the endpoints are both greater, so it must be coming down to a local min at 416 and 2/3. And we could check that that's a local min by looking at the second derivative, plugging that into the second derivative, and we should get what? No, not 0. Negative or positive? Okay, I haven't heard it yet.
Positive.
Why positive? Concave up, right? Concave up gives you a minimum. Concave up gives you a minimum. So if we were to take 416 and 2/3, all right, so this is the situation we have. Here at 25, we have the maximum value of 1250. Sorry, this should be 50 over 6. Okay, so at 25 we have the max at the endpoint. At the beginning endpoint here we get 625. And then we have this min. So it's got to look like this. If this is the only critical value and it's the lowest point, then we're expecting concave up. So if we took 50 over 6 and plugged it into our second derivative, it should give us a positive value indicating concave up, indicating local min.
How come it's always, how do you always know it's positive? Like what if it was like concave up gives it a negative?
All the second derivative is positive all the way through here.
No, I think she's talking about like the actual vortex is in the positive quadrant, not the negative.
Yeah. Can it still be concave up and then negative?
Sure. Down here?
Yeah.
Sure. And then if you plug that x value in, you'll get the second derivative as positive because it's concave up. Yeah, it doesn't matter. Yeah. The height of this doesn't change the second derivative at all. Does that answer it? Yes, ma'am. Chain rule, right? Because you're a master of the derivatives. You know that by the chain rule, you have to multiply by the derivative of the inside. You knew that. You knew that. All right, other questions? All right, let's do another one. A rectangular storage space is to be created against the building using 84 feet of chain link fencing. The fencing will comprise 3 sides of the space, and the building's wall will form the 4th side. The space must not be narrower than 4 feet. What configuration of the storage space maximizes its area? Okay, so lots of information here, and we need something to hold on to, some central thing that our goal is in this problem. What is the central feature of this problem?
Function.
What kind of function? Whose output is going to be what quantity will be the output of this function? What quantity? What are we trying to maximize or minimize? Area. So we need a function whose output is area. That's the central, everything in this solution will revolve around a function whose output is area. We need to get that function in one variable, and we need to get the applicable domain of that function. So you're going to try this. Take a couple minutes. So what do we need? We need function. Output is area. Okay? One input variable. And applicable domain. And then we're ready to go. We're ready to use calculus to solve it. See how far you can make it. Work together. We can walk around and help. Yeah. And so to do that, you're going to need a picture. Okay, draw a picture always when you can. Draw a picture. Did you have a question? Still thinking. Possible. Did you draw a picture? I think a picture would answer your question. So draw a picture of the situation. That will. Right? Sure. Okay. Label your quantities.
I don't know what the
There has to be a connection between what you did here and what you're imagining in your mind. Great.
and this is all
That's right.
yeah, but I don't understand referring to I don't know how to
So what's the focus of the problem? Is it focus of the problem that? Or is it focus of the problem that? A or B? Right. And now what do you have to do? One input variable.
What is it that was not the likewise storage space? I should make it like a real one.
Oh, really?
Sorry.
I think it's 8 because I think it's 8 because they're paying for work. Feet around the 3 sides. So they have this 40. So,
84 feet of chain link fencing. The fencing will comprise three sides and along the wall. You told me clearly here. You said here. That's right, 84 around those two sides. So what's the you need to label things like these can change that. These can change that. You got Y for that. So area, what do you need next? Is your function in one variable or two? That function in one variable. A of X or A of Y, it doesn't matter. Two.
Oh, yes.
It's 2 sides. Let's see. The question is going back from much.
Are you doing W or L? So W is going to be 84. So you have possible values of W. So you're saying that W can be 84. You're using the input quantity W, so you want all possible values of W. That's the domain. What's that? Let me do it. Okay, so there's different ways to define this. You can use length and width. I'm going to use X and Y. Okay, so what am I trying to do? I'm trying to maximize the area. Therefore, the whole function centers around this function whose output is area. So we'll start with a formula. What is the area? Length times width, so X times Y. Okay. So next thing I got to do is I got to decide what one variable am I going to use, X or Y? X is fine. Okay, so I need to write this A of X. So it's still going to be X times, then times what? So we need Y in terms of X. If I can get Y in terms of X, I'm going to put that expression right there, and I'll have that area function in terms solely of X. Okay, so how am I going to get Y in terms of X? Well, that's where the 84 comes in. So the amount of chain link fence that I have is going to be Y plus X plus Y is going to be my 84. So what does Y equal? 2Y equals 84 minus X. Y equals? What's 42 minus a half X? What's the central focus of the problem? This over here or this over here? The left or the right? This. All right. This is just the work that I need using that information about the 84. in order to write my function in one variable. So it's going to be x times y. What is y? We just found out that y is always 42 minus 1/2 x. Yours might be different, right? So if I did it a as a function of y, then it's going to look a little different. So if it was a as a function of y, then it would be x equals 84 minus 2y. So a as a function of y would be, just for those who did it that way, it'd be 84 minus 2y times y. So if you've already gotten this far, your function should look like one of those two. Both are correct. Okay, both are correct. So the first one is just using x as the input. The second one is just using y as the input. The solution will end up being the same in the end. Questions? Yeah.
Did you get the A of y from?
I just used, I found x in terms of y instead of y in terms of x. You don't have to do that. It's one or the other. Okay? But, so I did x in terms of y, which is x equals 84 minus 2y from this. And then I plugged that in for here, for x. So I did the same process again in my head. Okay?
Understandable.
Good. You just need one of those two. You don't need both. Okay,
Works.
what's next? We ready to start? No, not yet. We still need something more to this function. No. Applicable domain. Candidates come from critical values and endpoints. So you got to have the applicable domain in order to get the endpoints. So, domain. What we're saying is now we look at that value that we chose for the input and we say, what's the lowest possible x? Is 4 the lowest possible x? Yeah, it's got to be 4. So we could think about this getting taller and skinnier, stretching away from the building, and then the lowest possible x would be 4. Because it has to be no narrower than 4. All right? What about the biggest possible x? 80? No, not 80. Not 40. So the biggest possible x is when this is the longest and widest. And when it's the longest and widest is when what? When y equals 4. That takes up 4 feet here and 4 feet here, making x 76. Yeah, you were on the right track. You just need 4 feet for both y's. So if you did this function, your applicable domain was 4 to 76. If you did the other one, if I did a of y, the domain would be 4 to 40. If you did the other function, a of y, your domain for y would be 4 to 40. Because x would be 4, and you'd have 80 feet left. You'd have 40 for y there and 40 for y there. Questions so far? Okay, so now we want to find candidates. Candidates are going to come from one of two places. They're going to come from critical values and endpoints. Critical values. How do we get them? Take the derivative, set it equal to 0. At local maxes and mins, we get a pause in the accumulation. And where there's a pause, the rate of change is 0. Right? So we could do product rule here, or we could multiply it out first. That's easier. Much easier to multiply out first and just do it term by term. But if you want to do product rule on that, you're welcome to do that. So a prime of x equals 42 minus x. Set it equal to 0. Critical value is 42. Other candidates. Endpoints of the applicable domain. X equals 4 and 76. So now we know that 4, 42, and 76 are all possibilities for the maximum area and the minimum area. How do we tell which is which? We find the area for each configuration. A of 4 is 4 times 40. 160? Check my math. This would be 21 times 42. I'm not that good. What's 21 times 42? 882.
That's what I was going to say.
And then, what is this?
304.
304? Someone else get that? So now, when you get to this step, if you had the other function that I called a of y, you should get these same three numbers for the areas. 160, 882, and 304 square feet.
That 0 with 3 and 4 kind of looks like 6.
Okay, so how do we configure this chain link fence to maximize the area? So you figure it out. So how do we configure the chain link to maximize the area? Well, we need to know what these numbers mean. What is the 882? What does it mean? It's the area. What is the 42? Width. And how can you find the length? Or this y value? Well, here's our relationship of y in terms of x. So I think it's 21, is that right? So x is 42. We can use this to find y. Y is 21. And the max area is? In this configuration, 882 square feet.
Yep.
How do we get the minimum area? How would we configure this to get the minimum area? The real long wide one or the real tall skinny one? So is it the real long and wide one that gives us the minimum, or the one that's real tall and skinny sticking off the building? Well, we look at the minimum area is 160. So it's when x is 4. And y is? Is that our 40? Right. So that's when it's x is 4 and y is 40. That's the real tall, skinny one sticking off the building. That gives us a minimum area of 160. Okay, questions on this example? All right, let's get started on one more. Anybody have a question? Here we go. Harder. Listen, a square-based box shaped shipping crate is designed to have a volume of 16 foot cubed. Okay, the material used to make the base costs twice as much per square foot as the materials in the sides, and the material used to make the top is half as much as the sides. What dimensions of the crate minimize the cost of the materials? Okay? There's lots to do in this solution, but we need to have an anchor. What is our central focus of the problem? Everyone tell the person next to you, what's the central focus of the whole solution? Central focus of the whole solution.
Volume is still going to be 16.
I hear people talking about volume. Is it about volume? No.
Cost.
A function that what? No, whose output is? What? Whose output is what quantity? No, not the lowest. There's all kinds of costs. The whole point is we can choose lots of different inputs and get lots of different costs. Function whose output is cost. A function whose output is cost of this box. Then we're trying to find which configuration, which input value gives us the lowest cost. Okay? But the function, we need a function whose output is cost. We need that in one variable, and we need the applicable domain of that function. Go. See if you can. This is the hardest part. Coming up with this. The function in one variable with applicable domain. Go. Okay, so there is one kind of caveat to this. So the cost per square foot of the sides, the cost per square foot of the sides is unknown, but it's not variable. Okay, so you got to think of it. You're going to call it, say, K. Okay, so say the cost per square foot for the sides let's call it K. All right, it's unknown, but it's not a variable. So in your function, you may have the input variable, but then you may also have K, which is not variable. It's just a constant of.
So you get 16 feet cubed.
Yeah. How do you get cost from cost per square foot? So let's just get the cost of the base, or the cost of one side. What would the cost of, if I set my dimensions up this way, what will the cost of one side be? So we said K, the side is K, dollars per square foot. It's the sides.
Base costs twice as much.
Okay, so can you just get the cost of one side? If you set up the dimensions this way, can you just get the cost of one side? What would the cost of one side be? Anybody? Joey, what's the cost of one side? I know you don't. What's that? So K is dollars per foot squared. How are we going to get total cost if we have the unit cost, right? Cost per unit. So we got cost per foot squared. How are we going to get the total cost of one side? 2y. We need the area of a side, right? So we're going to take the total area of the side, how many feet squared it is, and multiply it by K. So it will be KXY. That would be the cost of one side, right? XY is the area, and then each square foot is K dollars. So we're going to take XY times K. And then how many sides do we have? 4. That's the cost of the sides. All right, what about the cost of the base? The base is twice as much, and what's the area? X squared. I'm going to multiply these. I'm going to add on the cost. So I got the cost of the 4 sides, and then the cost of the base, and then cost of the top would be half as much as K. And its area is also X squared. The top is also X squared. All right, and then if we wanted to get, let's do C as a function of Y, the height. Then we need to write X as a function of Y. What allows us to write Y as a function of X? What allows us to write Y as a function of X? This volume restriction. The volume has to be 16. So what's the volume of the box? 16 equals? Length times width times height. So Y is? 16 over X squared. Just kidding. I want to do C of X. Make it easier. So that means everywhere there's a Y now, I'm confined to this, 16 over X squared. There's the cost of the 4 sides in terms of just X. And then I can just, what is this here? This is X squared 2.5. So this is all 5 halves, KX squared. My K's are kind of funky here.
No worries.
K is just a constant. So the thing that we're changing is X, this side of the base. Okay? Domain. X could be as small as 0, but it's not very, we can make X pretty small here. And then X, well, so we can imagine this box getting bigger and bigger, and wider and wider and wider. If we make Y small enough, X could just get larger and larger and larger to meet this 16-foot cube. So there's really no upper limit. No. Because we can keep making Y, I mean, it's not realistic, but we can keep making Y small enough so that the base is as big as we want, and we get that volume of 16. So the domain is really not a player in this problem, all right? So 0 doesn't make sense, and a really huge, microscopically tall box doesn't make sense. So we're going to be looking for a critical value in this problem. Critical values. Not endpoints.
Picture of this?
Go, quick.
Very well.
All right, so here's what we'll do. Round 1 of these